So welcome everyone to our second spring HERMES heliospheric magnetic energy storage and conversion seminar. And today we have Victor Reville, who's in IRAP in Toulouse. And he's been working on solar wind and solar wind modeling and the role of turbulence and instabilities in the dynamics of the young solar wind. He did his PhD with Sacha Brun on asterospheres, and then he's been working. He worked for a while in UCLA, working on solar wind models for Parker Solar Probe, and now he's in Toulouse as part of the larger group that also does work on Solar Probe and Solar Orbiter. So I'll let you start, Victor.
Thank you, Marco, for the introduction. So thank you, everyone, for listening tonight. Tonight for me, of course. So today I'm gonna do an overview of my works these past few years. So mostly on the inner heliosphere. So I have actually a picture of the wind of a massive star, because it actually applies. I mean, some of it applies in the more broader context, but I'm going to be focusing on solar wind study, and you see here a fake image of Solar Orbiter and Parker Solar Probe, all together measuring the solar wind. And I'm going to speak about that a little bit. All right, so okay, so first, a little global introduction about the sun. So the sun is actually a solar-like star, like any other, which means that it's basically a low-mass star, below 1.4 solar masses. And all these stars, what they have in common is they have convective envelopes. And so you see, for instance, in this graph, you see the structure of all stars, from very low-mass stars to very massive stars. And when you have this red gibberish, is actually that you have you onset convection in the given layers. And so when you're below, okay, so here it's maybe 1.2 solar masses, you have essentially a radiative interior and a convective envelope. And when you go beyond this transition, you actually do the opposite. You have you change actually the nuclear reaction, and then they release more heat. And so you start convective to be convective in the cores and radiative in the envelopes. Right. And so on the Hertzsprung-Russell diagram, actually all the stars that do have these structures, they are highlighted here. So you see it goes from the red dwarfs up to stars that are slightly more massive than the sun, and the sun is right here. And actually it's a pretty large amount of stars. Actually it's the most populated kind of stars, especially M dwarfs. And so in general, studying the sun and the heliosphere is very important to understand the environment of all these stellar systems. Okay, so why am I speaking about convection and convective zone? Is because essentially in this convection zone you have dynamo-generated magnetic fields, which are, we believe in the sun, the effects of dynamo effect, and especially alpha and omega dynamo effects. So in the sun you have so the convection zone is actually in the differential rotation. So you rotate faster at the equator than at the pole. So you see, for instance, an image of the rotation frequency obtained by helioseismology. And so what it means is that when you have poloidal field, because of the differential rotation, you will essentially create a toroidal field from poloidal field. And then to restore, let's say, the opposite, so create poloidal from toroidal field, you need to have what is called the alpha effect, which is essentially due to convection and turbulence. So there's already turbulence inside the envelope of the sun. And I'm going to talk about turbulence in the solar wind right after that. Okay, and so all these stars, they have a dynamo-generated magnetic field, and we observe them to have a hot coronae, especially in the X-ray. And by hot, I mean 1,000,000 Kelvin coronae. So for instance, here you have a parameter, which is a Rossby number, which accounts for, at the same time, the rotation rate and the thickness of the convection zone. And essentially, when this number is becoming smaller and smaller, the stars becomes more active, which means that essentially stars that are less massive, they are more active, and stars that rotate faster are also more active. Right. So for the sun, this is what we have. We have the solar granulation with these magnetic structures, magnetic concentration in the dark spots, and we have the million Kelvin solar corona that you can see with this image of the eclipse, with the salt and pepper patches on board, and these active regions that we can see with the superposed magnetogram. As a consequence of this hot corner, we have the solar wind. And I mean, the very simple idea behind the solar wind is essentially a very fastly conducting plasma and the spherical geometry and the central object with gravity. So when you have all these, you add all these ingredients together, what you get is this Parker diagram, which is very famous, where you have the solar wind solution that goes from subsonic to transonic solutions. So this is the Mach number essentially, and this is the radius divided, normalized by the critical radius where the wind becomes supersonic. So this is one here. Then you have this accretion solution. So you need to look at, let's say, from the other way. So going from the large distances with flow that actually are increasing in speed and then eventually end up creating a shock. And then below you have this breezy solution that was discussed at the time of Parker when he introduced first this diagram and claimed that actually the solar wind was in supersonic expansion. So now when we look at, I'd say, the fate of this hot corona among these, let's say, family of solutions that we can obtain doing the math, essentially, we have only the supersonic wind, the accretion, and the accretion breezes, because all the other solutions are either non-physical or they are unstable to acoustic perturbation. And this is a paper by Marco. And essentially, what is going to determine the eventual fate of the system is the hysteresis, because, for instance, if we play with the pressure at infinity, so very far away. So if we have a zero pressure, we will have the classical wind solution, so expanding and supersonic wind, and then we start increasing this pressure, and we will consequently create a shock, and this shock is going to be going inward and inward as we increase the pressure at infinity until we reach this critical wind solution. And once this critical wind is reached, when we keep increasing the pressure at infinity, actually what we create is a reverse flow and a shock accretion. And then when we relax this pressure and we allow it to become smaller, we will go to a critical accretion again, and then to accretion breezes. And in the end, this is how this system is expected to behave. Of course, in the solar wind and probably in most stars, I mean, for the sun, the solar system, and probably for most stars, the right solution on the mate sequence is the usual solar wind, actually, with a shock at the end. And even though all I said was the consequences of hydrodynamic equations, we know for a long time that the solar wind is controlled by the magnetic field. And you see these pictures of the Ulysses spacecraft. So the confirmation that the solar wind was actually supersonic came from two spacecraft, Luna from the east side and Mariner for the west side. And now we know that actually we have essentially two components, the fast and the slow wind, that are correlated with the magnetic field structure. So here, for instance, at the solar minimum, you see the speed, wind speed, as a function of latitude, and the color represents the magnetic field polarity. So what we observe is that we have fast wind at the poles and slow wind around the streamer belt and close to the closed field regions of the sun. And then when we are at maximum, we're essentially a closed field structure all over the place, and we have fast wind and slow wind all over the place equally. And then we have the Ulysses third orbit with the reversal of the cycle. And then we see that we come back to the structure of bipolar structure of slow and fast wind at the poles and at the equator. So as I said, the wind expands up to about 100 AU and then ends with a termination shock. And we now know that some of the probes that we sent in the 70s, they probably have passed the termination shock after more than 40 years of travel. And so you see them like going outside the termination shock and in the helio pose, where you have actually a mixing of elements from the interstellar winds and the solar wind. Right. So now the key question that, I have not answered yet is how to convert the sun's convective energy into heat. And as my talk title probably was announcing it, the hypothesis I'm going to be focusing on is turbulence. And the reason is that we have many years of observations of the turbulence in the solar wind. And for instance, here I show a very famous picture by Bruno and Carbon in 2013, where I have the spectra of the density perturbation or the magnetic field perturbation in the fast wind and in the slow wind as a function of the distance. So first, what we notice is this range in green for both slow and fast wind, where you have essentially slopes that are close to f to the minus 5/3 or perhaps f to the minus 3/2, which are essentially what we expect from a Kolmogorov phenomenology or Hiroshnikov-Kreshnan. Then, of course, what we have also is that the energy decreases with distance. And actually, this is not really due to dissipation. This decrease with distance is very consistent with the WKB expansion of the perturbation. The clue, however, that we have dissipation in the cascade is in this f to the minus 1, and especially in the location of the transition between the f to the minus 1 and f to the minus 5/3 spectra. And okay, we know that there is a cascade because essentially this point moves inward in frequency as we go further and further away from the sun. And of course, we expect the solar wind to be turbulent because it's a very large Reynolds or Lundquist number system. So this is something that we expect. It is, however, very close to the hydrodynamic phenomenology, and this actually, I think we don't really understand why yet. Okay, so we have this f to the minus 5/3 slope, and yet it's not really hydroturbulence. And the reason is that at least in the inner heliosphere, very close to the sun, we are in the low beta plasma. And so, for instance, like typical instabilities like Kelvin modes, they are going to be quenched by the magnetic field. And to show this, to illustrate this, what I've done is just a simulation, very simple simulation of a Kelvin modes with a guide field in the x direction. And what is funny with this movie is that you kind of see the turbulence starting and then being stopped by the magnetic field. So in principle, we are not expecting, and as I said again, it's likely, at least in the inner heliosphere, to have typical and regular HD turbulence. So we have other processes that are working to create the turbulence spectrum. And we have, let's say, dynamic studies directed along magnetic field lines. And somehow we know that this turbulence cascade must be produced by, let's say, a 1D process or processes that are occurring along magnetic field lines. And of course, one of the major hypotheses is that we have counter-propagating alpha waves that are interacting non-linearly and creating this cascade. So for instance, here you see a simulation, recent simulation of the onset and the creation of a turbulence scales from two population of counterpropagating waves. Right. So if we put this into equations, what we have is that we usually use the SSR variables, the Z plus minus, which is, this is the way I define it now, but there are many ways to define them. But if you want to study the perturbation, let's say in the most intuitive way, perhaps this is a good formulation. And we write that it's equal to the perturbation of velocity minus plus the sign of the guide field, here it's BR for instance, times the perturbation in the magnetic field normalized to an alpha velocity. Okay, and so essentially here plus is a forward wave, assuming that you have a positive polarity, and minus is an inward wave in a positive polarity as well. And it's the opposite when the sign of BR changes. Right. And now, when we write the reduced MHD equations, which means the incompressible MHD equations for these variables, what we have is we have three terms. A first term, which is, okay, so you have of course, the temporal variation here, dz plus over dt. And then you have this first term, which is the propagation, and essentially the WKB theory. And this propagation, so you see this, for instance, V plus VA times nabla of Z plus. Okay, so it's essentially the wave that's propagating, but it's also acting on the flow, and I'll come back to that in a few slides, through a wave pressure. So that's everything in this part. The second part is a reflection on gradients. And you see here that you change sign here in the Z plus term. You have a Z minus plus here and Z minus plus here. And what is creating these reflections is the gradients of the afferent speed and the fluid velocities. And for instance, here I show a typical profile of the afferent speed and the temperature in the solar atmosphere for different cases. So for instance, you have CH1 and CH2, these are coronal holes, so open solar wind solutions. But you have also loops with the LO1 and LO2. And you see going into the transition region, you have these strong gradients at the transition regions and beyond of the alpha velocity, for instance, and you have a maximum of alpha velocity around, let's say, 1 solar radii after the surface. And the last term, of course, is the nonlinear interactions and the cascade, which is wrote really simply here, but which is essentially responsible for the heating of the solar wind in this theory, right? So if we look at now the origin, because we have transport equations, we have propagation and the cascade, but we have to create these alpha waves. And here I would like to remind the beginning of my talk where I spoke about convection. And essentially, we still believe, even though perhaps switchbacks are going to change this picture, perhaps quite a lot, that the convection motions that we see in the chromosphere, for instance, here you have pictures by Inode of spicules. They could be the origin of the FN waves that we see in the solar wind. We have, for instance, typical amplitude, sorry, there's the video bar here, but typical amplitudes are 20 kilometers per second. And typical periods, they are of the order of the minutes or 5 minutes, for instance, which is believed to be the peak of the distribution. Just to illustrate, there's here a simulation of the chromosphere made with the Bifrost code, where you see the structure of the carpet that is creating these oscillations in the chromosphere. Okay, so now I'm going to go to the Parker Solar Probe mission. So I guess many of you are familiar with the mission, so I'm not going to spend a lot of time on it, but still, so it's been out in the inner heliosphere for now about 3 years with essentially 4 instrument suits. which are fields, sweep for the magnetic field and the particles, and then ISIS for the energetic particles, and WHISPER, which is a white light imager. So already at the first orbit, it was already the closest and fastest spacecraft that was launched by humanity, the closest to the sun. And the ultimate objective is to go below 10 solar radii. So there's a radii that's missing. And the reason is that we want to go below the RFN surface. If I come back to the equations here, you see that the propagation speed of these variables, there are V plus VA. And so essentially, when you are below the RFN surface, you have the counter-propagating wave populations. So we expect that most of the turbulence is generated below the surface, and we believe it to be, say, below 15 solar radii or even below 10 solar radii. So that was, I think, what set the objective of the Parker Solar Probe orbits. And you see here in time, so I think it's a bit outdated now. We've had here about 7th encounter. And essentially what we do with the Parker Solar Probe to reduce the distance of the perihelion is to do a Venus gravity orbits, gravity assist, sorry. And so each time we do this gravity assist, we get closer and closer. And so the first orbit we were at 37 solar radii, then we went to 27, and now we are actually around 20 or even below 20 solar radii. And in 2024, if everything goes well, the Parker Solar Probe will be around 10 solar radii at the perihelion. Right. Okay, so this was the introduction, essentially. Now I'm going to talk about essentially what I did with colleague, of course, but and what I did was to develop an RFN wave turbulence 3D MHD model, which accounts for the RFN wave transports and the dissipation. So what you see, essentially not in blue, is the usual MHD equations. And I've added to that the physics of RFN wave propagation, and especially of the energy of the RFN waves packets. And these are the E plus minus that you see there. And what I kept from the previous equations is essentially the WKB part and the dissipation. Okay, so you can see the relation between the Z plus minus and the E plus minus. So the E plus minus is just the energy density of the waves. And the dissipation here is following what we call a Kolmogorov phenomenology. So we have this term, which is the nonlinear term, which is obtained from a dimensional analysis of the nonlinear term that I was showing before. So you have the heating and the cascade, which is E plus minus squared, because we're actually looking at the energy, so the moments of the RFN wave equations, times the Z minus plus. And the reason I'm adding this term is to have an implicit reflection with a coefficient of 0.1 for a reason that I can explain later. Okay, so the code is based on an open source code, which is Pluto. And this physics of the RFN wave propagation, this is what I've essentially added to the model. In addition to the RFN wave seating, we have also a volumetric heating that we can parameterize, and of course thermal conduction and radiation. The radiation is essentially optically thin, so we don't. It's just a function of the density and the temperature of the plasma in the inner atmosphere. Right. Okay, so just a few technical stuff. So in the Pluto code, we thus have two new equations. We have equations for forward propagating waves in positive and negative polarities. And because they are pure RFN modes, we don't have to change the diagonalization of the system. And so this is very suited to codes like Pluto, which are Riemann solver codes. And we can use, for instance, HLL or HLD solvers in the code. what we have also added is this special, let's say, way of treating the thermal conduction with a collisional term first, low in the atmosphere, and a collisionless term. Essentially, there's a transition that is occurring around, at around 5 solar radii, and we go from a classic Spitzer-Harm collisional thermal conduction to a collisionless, which is proportional to the temperature and the thermal velocity of the particles. We have also a trick to treat the transition region, especially when we do 3D runs to thicken the transition region. And this is based on, sorry, I have not mentioned it. This is based on the work of PSI, especially a paper by Roberto Leonello in 2009. Okay. So now I'm going to try to join the two things I've mentioned, i.e. Turbulence and Parker Solar Probe. And what we did actually in 2020, when I was at UCLA, is to look at the first data of the probe and to try to run this model against it using a magnetic map. So if you will, the input parameter of this model is are just the magnetic map, the amplitude of the perturbation, and for instance, the correlation length of the turbulence to control the level of heating that we set in the code. So you have a lot of panels here, but you have the magnetic field, radial magnetic field. You have the total magnetic field, the velocity, the density, and then you have some other quantities like the momentum and the azimuthal velocities. And the vertical lines, there are the HCS crossings. So when the probe was actually seeing another polarity for the magnetic field, not accounting for the switchbacks, which are all these structures that you can see here, for instance, at the period, where you have a positive magnetic field, but you do not have, per se, a crossing of the HCS. I mean, you do not have at all a crossing of the HCS. Okay, so in red now, what I'm showing is the results of the model. So what it's interesting is that we only used one single map, and this is a 40 days, 45 days interval. So actually, we got lucky because the sun was very quiet at this time. I mean, it's not something that is easy to do anymore. This is something I'm investigating right now. But at the time, it seems that, I mean, from a single observational input of the map, which was taken on the 6th of November, which was the day of the period, we got a good agreement between the data and the model, essentially. So you have in red the HCS crossings that we had, and the only thing that we missed is those dashed lines, which is an HCS crossing that we actually missed in the model. And the reason is because of the time evolution of the solar magnetic field. But for the rest, I mean, we have a really good agreement. But for the azimuthal velocities, and I won't speak too much about this today, but I think this is still a really open question on whether, I mean, how can we explain those velocities? This is still very open. Okay. So although we do reproduce the average tendencies, of course, we do not have the fast evolving structures, the waves, essentially, because the waves are accounted for in a subgrid manner, in the sense that we are accounting for the energy of the waves. But if we look closely, actually, the perturbations in the magnetic field, especially, what we can see here, for instance, is the magnetic field data taken at different time averages. And the largest time averages, which is the red curve, is actually nicely corresponding to the field that is obtained in the simulation. Here it's as a function of the distance, which means in the sense that we do capture the average magnetic field, and that the rest is perturbation, and especially switchbacks, because we have perturbation in the radial field. And here what's is very, very intriguing is that when we plot the amplitude that we expect for the perturbation at this at a given distance, we really reproduce the envelope that was observed by the probe at the first period. So what it means essentially is that first, the amplitude of the perturbation that we have in the model is consistent with the data, but also that the switchback that probably are part of the solar wind turbulence, because there is an energy budget argument here. We need this amplitude to power the solar wind at this level. So if we find switchbacks to be at the right level, then it means that they are contributing to the solar wind turbulence in some sense. Okay, something else that I did was just to compute the sources of the solar wind with the model. And what you see here is synthetic emissions. So you have dark regions that are coronal holes. And during the perihelion, we had the Parker solar probe connecting to this equatorial coronal hole that we see here. And this is consistent with other models like PFSS modeling, for instance. All right. So this is what we can do with the 3D global MHD models. However, there are many things that were like put under the carpet. And one of them is actually the problem of the wave frequency. When we do these 3D global approaches, we do not account for the fact that essentially the reflection mechanism is frequency dependent. And with waves, typical waves excited at the minute timescale, the reflection is not very efficient. And if we look at this spectrum of the solar wind, we have here typical injection frequency, for instance, in the chromosphere, and the interval where the reflection is efficient is at much lower frequencies. And so the question is, in general, is how to create these low frequency alpha waves in the solar wind to enable the reflection mechanism to act and to create the cascade. And to answer this question, we developed actually 1D simulations where we used again the Pluto code, but this time in a so in a flux tube configuration where you have a profile, but you have the 3 vector components for the velocity field and for the magnetic field. And we forced them from the inner boundary at the typical frequencies for the speckle, a few hundred seconds and a few kilometers per second. And if I show a movie, so you see the structure of so you have the speeds, the FM speed. Here you have the wind speed, the sound speed, you have the temperature, so going to the transition region. And when I launch the waves, at first they start to follow this gray line, which is the WKB profile. But then something happens. You have, I mean, it's not so clear in this panel, but if you look at the wind speed and at the FM speed, you see that there is some perturbations, and actually there is a compressible process occurring. And this compressible process is the parametric decay instability. So if we look again at another movie, we see this process. So we have the forward wave, which is here Z minus, which is propagating in the solar wind. And we have the onset of the parametric decay instability now, where you have this strong decay of the forward wave, and you have the creation of an inward wave, along with compressible perturbation in delta rho and delta V. And if we look at the spectrum of these perturbations, so we actually realize that it's a 3-wave process, where you have a forward Alphen waves that decays into an inward Alphen wave and a sound waves, and those 3 waves, they are in resonance. So it means that we have the frequencies of the outward Alphen wave, which is equals to the frequency of the sound waves plus the frequency of the inward Alphen wave, and the same for the wave vector. And in general, what we have is that the inward Alphen wave has a lower frequency than the outward Alphen wave, which is what we can see here. For instance, you have the mother wave, which is here at maybe 7 on the scale, and then you have the sound wave here at 12, And then you have the inward Alphen wave here at 4 in wave vector, normalized wave vector. And so we do have an inverse cascade, which means that we are able to create a low frequency from, say, from the typical frequency of speckles in the chromosphere. And so, for instance, here I show two cases. One case when we are stable. So, I mean, depending on the amplitude of and the frequency of the wave, you are either stable or unstable to these processes. But when we inject the waves at 200 seconds or 100 seconds, we are almost always unstable. And we can see that we can create a almost fully developed spectrum from this process in the unstable case very fast. And we can create these low frequencies here in the simulations. Whereas when the case is stable, we have essentially a monochromatic input, which says monochromatic. So these spectra, they're actually made at 10 solar radii. So it's already after some propagation in the solar wind. And what we have is that we also have an inward Alphen waves, but at much lower level than in the unstable case. And so, as I said, we create a fully developed spectrum, which has a typical compressible slope of f to the minus 2. Okay, so this is one answer we can, I mean, essentially what I want to show here is that when you look in the details, you have to associate different physical processes and especially instabilities to explain what happens in the details. Even though the turbulence formulation is very efficient on the global scale, there are still many things to understand. And to finish, I'm going to talk about recent works about flux ropes and another instability, which is the Turing instabilities, and the association with the periodic density perturbations that we have in the solar wind. So, I mean, you may know these pictures. So what we see here is essentially blobs or density enhancements that we can see ejected from the sun. So the sun is here, which are propagating towards the outer heliosphere. And usually these blobs are detected in heliospheric images. And they have scales that go down to 1 solar radii, or perhaps even lower, with probably a discrete spectrum. So it means that we have, it seems that these processes have preferred frequencies. So for instance, here there is a paper by Nicky Vial, where you see peaks at 5 hours, 3 hours, a peak at 100 minutes, which I'm going to be actually very interested in. And you have also longer frequencies at 10 hours, and perhaps also other peaks below. So, I mean, the general idea is that these streamer blobs are created basically at the tip of helmet streamers in the sun. And the tip of helmet streamers, they have both strong currents and also velocity gradients, because you have slow wind around the current sheet, and then you have probably fast wind a bit higher up. So in principle, they could be that could take place, but it was shown quite early on in 1999 and 2005 by Giorgio Einaudi and Franco Rapazzo, that actually, I mean, we don't expect helmets to be happening here because we have expansion that stabilizes. And so we are essentially left with resistive processes, and especially the Turing instability, and the processes of fast reconnection. So here I want to say that when we do simulation of fast reconnection, we have to be extremely careful, because we are obviously not in the right regimes when we are doing MHD simulation, and especially large-scale MHD simulation. And I mean, what we can expect from simulation is to have Lundquist number of 10 to the 4 or 10 to the 6, where in the corner we have 6 order of magnitudes higher. And it's very key, because depending on the behavior of the reconnection process that you have very different behaviors. Okay, what did I say? Sorry. Well, anyway, so the first question was to show if we could let's say develop some scalings as a function of the Lundquist number, and to see whether we could fall into the sweep-up curve, for instance, or the ideal tuning scenario, which are a reconnection scenario developed by the ideal tuning by Vuvapucci, Marcovelli, and Anna Tonari, for instance. And so we did a parametric study using the same code that I showed before, but with a very simple configuration, a simple dipole magnetic field with the current sheet at the equator. And of course, we use a resistive version when we can control the Lundquist number. And the first thing we showed is actually that we do follow the thickness. I mean, the reconnection is triggered with an aspect ratio that is close to a scaling of s to the minus 1/3. And this is what you see here. You see the current sheet before the reconnection. So if the Lundquist is low enough, there is no reconnection. But when you do increase the Lundquist number, or let's say about 2 10 to the 4, 3 10 to the 4, then you have reconnection starting from this point. And then the aspect ratio that is reached before the onset of the tuning mode is following this instability in this scaling, which is very different from the s to the minus 1/2 scaling. And so this is very interesting because the ideal tuning scenario predicts the evolution of the fastest growing mode of the tuning instability. And for instance, it predicts that it grows as s to the 1/6. And this is what we measured in our simulations, up to large Lundquist number, 10 to the 6. And for instance, okay, so you see in these two simulations that you have different fastest growing mode for different Lundquist number, and you go to smaller scales and you go higher in the Lundquist numbers. But we can extrapolate this fastest growing mode to very large if we follow, let's say, the asymptotic theory of the ideal tuning scenario. Okay. So here it's a movie of the process, and you see actually the tuning mode that is triggered here, but it's not triggered only once. It's actually triggered in this video 3 times. And what we observe actually that is very interesting is that we have several onsets of the tuning instability that are separated with longest, let's say, longer intervals. So you have, for instance, here you have 3 onsets, which are shown here with the exponential growth of the FN speed in the theta direction. So this is the spectra here in the Fourier space. And you see this is the instabilities here that are triggered. And then you relax to a quasi-stable state, and you trigger the instability again and here again. And in between these onsets of the instability, you have flux ropes and blobs that are propagating, typically at the frequency of the fastest growing mode of the instability. So we get 2 time scale, a long one, 30 hours, and a smaller one, which is related to the tuning mode and the fastest growing mode. And if we extrapolate these scalings at higher S, we get, let's say, about 80 minutes frequency. And so we are close to the observations in the solar wind. Okay. So here are my conclusions. So affine wave turbulence, it offers a global understanding of the coronal heating. So we do, I think we have now a pretty consistent and convincing picture that the turbulence is largely involved in the solar wind acceleration and the coronal heating. Although, I mean, there may be other processes that occur, but the general picture is here. And we have developed a 3D MHD model that is able to reproduce a lot of the in situ and also remote sensing observables. For instance, the EUV image that I showed, they actually also compare quite well quantitatively with the EUV images made by AIA. But if you want to look in the details, we have to care about a lot of different physical processes. and especially instabilities that are making this this picture possible. And today I only spoke about fluid instabilities, but there are almost an infinite number of instabilities and kinetic instabilities that also allow for this say MHD fluid model to be to even make sense. So there are a lot of things to dig and to work on. And Parker Solar Probe and Solar Orbiter, they are very, I mean, they are a unique opportunity to study all these fundamental processes and plasma physics in general. So thank you all, and please ask questions. There are things that I missed or didn't understand.
Thanks, Victor. Let's open the paper for questions. I'm sure you'll get a few. I have my own, but of course, I'm going to let other people ask questions first. Go ahead. Go ahead. There's a lot of things to criticize. Cooper Downs.
Well, unfortunately, I'm not going to criticize it. I think this was a nice way to summarize all this stuff, and especially going from the global 3D modeling to showing how there's physical processes underlying that that's not in the fluid models. So kind of on that theme is, obviously at PSI, we do a lot of the global modeling as well. And I'm sort of finding that this basic approach to wave turbulence, it's okay. But then when you start looking at the quantitative details of comparing to observations like the temperature in the corona or charge states or solar wind speeds and densities, getting it better is challenging. So in terms of, with your experience looking at these sort of more detailed turbulence experience, what do you think is the next direction? Like, how do we improve these global models? What's your perspective?
Yeah, it's a very good point. Yeah, as you said, it's I mean, it's not easy to get the picture that we are at. It's already pretty difficult, but the next step is even more difficult. I fully agree with you. And for instance, one very tempting approach is to start incorporating some kinetic aspects to it, either by having a parallel and perpendicular temperature, which I've not explored so much, but I know other groups have. For instance, the Michigan group. But then it involves a lot of also assumption of the way you treat, for instance, kinetic instabilities, and the way you limit the ratio of parallel to perpendicular temperatures, and this sort of thing. So I think really the way to go is to advance, like at the same times, the detailed studies of either fluid or kinetic codes and the global modeling of the corona. And if we can have, I mean, both approach at the same time, we can probably, yeah, I mean, learn a lot more and trying to improve these kind of models. But I mean, I don't think that 3D MHD modeling is meant to do everything. I mean, we should be humble in some way to what these kind of models can do, even though they are I mean, remarkable also in some sense. Just having one single observable of the magnetic field and to be able to reproduce so many variables, I think it's already outstanding. But yeah. So
thanks. I think we then have.
Thanks.
I think we then have Bimson.
Thank you, Marco. I got a comment to ask first. The 3D, so the parametric driven, so parametric decay instability, it looks like the Brillouin scattering. You know, you are French, so you know that name better. Brillouin scattering with alpha mu replacing the electromagnetic wave.
I'm not sure I'm familiar with this.
Sorry. Because there's Raman scattering, Brillouin
scattering. Raman scattering.
Yeah, okay. My question is, you mentioned in connection with the turbulence generated by the PDI, that there is this typical f to the power -2 spectrum. Are you referring to the Kodomtsev-Petriashvili spectrum by chance?
No, I think in 1D, essentially you will create the nonlinear interactions by shocks in.
Yeah, that's a shock spectrum. That's right. Yeah,
so this is why you get this kind of spectra in this structure.
I thought because that was the original idea of a Kodomtsev-Petriashvili shock model of compressible turbulence. and they came up with this F2 power minus or K to power minus 2 spectrum.
Yeah.
Go ahead. Thanks.
Thanks. I hope I don't mispronounce your names. We have Hui Li.
You got it right. So thanks for a nice talk. I have a quick question on the PDI. PDI has a kind of a beta dependence and threshold.
Yes.
Did you purposely choose some lower beta and larger?
No, because the inner heliosphere, the low corona it's low beta, so we didn't have to do anything. We used what I would call very realistic profiles of the solar wind, and we just launched the waves from the photosphere, and it really happened like easily. This is why I think it's very likely that this process occurred in the low corona. There was really not much tuning to work to have it happening.
Yeah. So at a higher frequency, you generate those multiple peaks that looks like quasi-periodic signals. Do you foresee those?
Oh, okay.
So preserved going out to where Parker can measure?
So you mean these kind of things? Yeah. Okay. So I didn't have.
Or even the lower right ones. Yeah.
Okay. All right. So these are essentially harmonics of the fundamental frequencies, I think. So in this study, what we wanted to do is to identify precisely the mother waves and the daughter waves and compute the growth rates and et cetera, et cetera. So we used either monochromatic spectrum or spectra that were average on the main frequencies, and this is why we have these harmonics. But this is not something that I expect to be in the real data. I mean, it could be if we do have a very let's say singular pit of the excitation of a speckle, for instance, it could be very close in. But in general, I think turbulence will take over very, very quickly.
Okay, thanks.
Thanks. Any other questions or comments?
May I ask one quick question?
Please do.
Victor, nice talk. So my question is related to the reflection coefficient for these alpha waves, and probably I think one parameter is your, the scale length of alpha wave versus gradient in alpha speed. So what else controls this reflection coefficient?
Okay, so the reflection coefficient is actually in some way it's a parameter of the model. It's not related to the correlation length scale, which is another parameter that we can choose. But the reason I've chosen this 0.1 value is was looking at analytical models of this kind of incompressible reflection processes. And for instance, I compared here in this slide with the model of Chandran and Holweg, where you have the a non-WKB theory for the reflection of the affine waves. And what we have is that in most, it's a very large part of the low corona, which is here we have the effective reflection, which is close to 0.1. And this is why I choose this. Knowing that this part is probably known, it's not really realistic either for in our model, but also in this model by Ben Chandran. So yeah, those are two different things, but of course both will have consequences on the solar wind heating. But 0.1 is just it works, but it's also a simple, just a simple value and perhaps arbitrary, but yeah.
So what can you change to make it, let's say, 0.5? I just want to get some intuitive feeling, like what really controls this reflection coefficient.
So in principle, what controls it is the gradients of the affine speed and the velocity field. So it will change as you go higher in the corner. But the reason I didn't spend like I don't want to go too much into these kind of details, or at least as far as 3D MHD modeling is concerned, is because I mean, from the for instance, from the turbulence compressible turbulence study that I showed, I know that I mean reflection is not the only thing that happens, especially low in the corona. So my approach is, yeah, it's really to yeah, to advance both ways. As I said to Cooper, is to I mean, you can do models of more complex reflections that are related to the gradient of the Alphen speed, but in the end, it's not even clear that it's really what's going to matter for the realness of the solution. So, I mean.
Okay, thanks. Maybe I can ask, you know.
So I mean, it's a very profound question. There's many things we could discuss about.
I mean, this is one thing we kind of struggle seeing this stuff in experiment. That's why I was trying to get a better insight. I can ask you later in more detail.
I remember, Krista, from some of the experiments that I've seen, actually the Alphen speed became very low, and there was essentially no transmission on one side, at least from a poster that I saw a while ago on an LAPD experiment.
Yeah.
Yeah.
But this is I think, a very important point. So
right.
That's why I thought.
Yeah. Okay, thanks.
Yeah, thanks.
Any other questions or comments? Don't be shy. All right, well, if there are no other questions or comments, let's thank Victor, and we'll see you again in about a month's time, third week of May, and with a new heliospheric magnetic energy storage and conversion seminar, third week of May, Wednesday. Thanks very much, everyone, and talk to you all later. Bye.
Good afternoon. Bye.
Thank you.